Inside every nuclear fuel rod is a self-tightening brake with no moving parts. The hotter it gets, the harder this brake clamps down. No computer, no operator, and no emergency system has to touch it. The laws of physics just refuse to let the reaction run away. To see how this brake works, look at what happens when reactors fail. We've all seen the movie version. The needle spins into the red, alarms blare, and the whole building goes up in a fireball. But that isn't how these machines actually fail, because physics builds the difference right into the fuel. And that's the secret most people never learn. In 1979, 3 Mile Island suffered a partial meltdown. A stuck valve let coolant escape, the operators misread their instruments, and the core partially melted. But the chain reaction had already stopped. But Fukushima in 2011 tells the exact same story. And it proves this wasn't a one-time accident. The earthquake triggered an automatic shutdown, and control rods slammed into place within seconds, so the reactors weren't splitting atoms anymore when the tsunami arrived. Decay heat melted the fuel because the cooling was gone. Hollywood shows atoms splitting faster and faster until the whole thing detonates like a bomb. But a power reactor isn't built that way, because engineers deliberately arrange the fuel so the hotter it gets, the less efficient the chain reaction becomes, and the reactor wants to settle down instead of accelerating. So a meltdown isn't a runaway chain reaction at all. We're talking about a cooling problem. The physics has already shut the reactor down, so the real danger is heat removal, not the atoms running wild. That's the distinction. Inside the fuel, uranium atoms split apart and release neutrons that hit other atoms. This chain reaction is the engine of the whole reactor. And physicists track its balance with a simple number that sits at 1 when the reactor holds steady. If the number climbs above 1, the reaction grows, but if it drops below 1, it dies out. The whole trick is keeping that number pinned at 1, because tiny shifts can mean the difference between steady power and an emergency shutdown. Engineers design the fuel so when the temperature rises, the reaction automatically slows down. The hotter the core gets, the more the physics pushes back against the chain reaction, and it works just like a self-tightening brake on a wheel. The faster the wheel spins, the harder the brake clamps down. This behavior is called the negative temperature coefficient, the hidden law that keeps the reactor from racing away. The fuel is an active feedback system that the atoms create on their own, and that feedback happens faster than any computer or control rod could react, because the atoms act like first responders that never take a break. But a lump of metal can't think, so the feedback comes from the atoms themselves through Doppler broadening, which is the sorting trick that makes the whole system work. To understand it, you need to see what uranium actually does inside the fuel. Most of the uranium inside the fuel isn't the kind that splits apart easily. More than 99% of it is uranium-238, which doesn't split when it catches a neutron, but is hungry for neutrons at specific energy levels called resonances that act like narrow traps. When the fuel is cool, these resonances are narrow energy windows. They only catch a few stray neutrons, but when the fuel heats up, the atoms start vibrating faster, and those resonances smear wider through Doppler broadening, which chokes the reaction. Uranium-238 absorbs more neutrons. The wider resonances mean those neutrons never reach the uranium-235 that drives the chain reaction. So the hotter the fuel gets, the more neutrons get stolen away by uranium-238, and the reaction slows down automatically because of a direct physical law, not an engineered system. The water flowing through the core does more than carry heat away. It also slows neutrons down so they can actually split uranium-235, and that adds a second layer of feedback. As the water heats up or starts to boil, it becomes less dense and slows fewer neutrons. That means less fission and less heat, so the reactor chokes itself out on 2 different levels at once, all without any human input. Doppler broadening happens instantly. It occurs before any safety system or control rod can react, which is why engineers call it a prompt negative feedback effect. The atoms act like first responders, and they don't stop or ask for permission.
Of course, there's one exception.
The RBMK reactor at Chernobyl used a graphite moderator with water coolant, and it was so over-moderated that when the water boiled away, the graphite was still slowing neutrons, which meant removing coolant made the chain reaction stronger. That's a positive void coefficient, the exact opposite of modern reactors. Engineers design modern light water reactors to be under-moderated. Any loss of water automatically weakens the chain reaction. Regulators require negative temperature and void coefficients by law, so no one uses the RBMK design anymore, and the physics is on your side in every reactor running today. But reality is simpler than the movies make it look. The real danger in a nuclear plant has never been the chain reaction running away, because it has always been the heat left over after the reaction stops, and that heat builds up for days. Even when the atoms aren't splitting anymore, the fission products keep producing decay heat. If cooling fails, that heat can still melt the fuel, which is exactly what happened at Fukushima when the tsunami wiped out the backup power and left the reactors with no way to cool down. The physics stopped the chain reaction perfectly, but the engineers couldn't keep the water flowing. So a modern reactor doesn't run away, the fuel itself refuses to let it. The negative temperature coefficient is a physical law written into the atoms, and it never fails when the core overheats. Without a single switch a human operator has to flip. The reactor doesn't run away because the atoms themselves refuse to let it. That's the hidden logic inside the machine, and it's built into the physics, not the engineering. If you want to see more of how the world actually works, hit subscribe, because we take apart the hidden logic inside machines, one breakdown at a time. Thanks for watching, and I'll see you in the next breakdown.